All right, so welcome to lecture 21 of this course on algebraic topology. Today we're going to talk about the two-hole torus and the three crosscaps surface. So what I want to do now is take the hyperbolic geometry that we've very briefly sketched in the last lecture and show how a lot of the surfaces, all the ones with negative Euler characteristic, can be put into a framework within hyperbolic geometry. In other words, given a geometry that's essentially hyperbolic, at least locally. And what we're going to really use here is a fundamental and deep fact, is that there are a lot more symmetries in hyperbolic geometry. Than in Euclidean geometry or in spherical geometry. The group of symmetries is richer, and that translates into there are many more interesting tessellations. So a tessellation is a covering of the plane with the same polygon repeated. And usually we're interested in regular tessellations where the polygons are reasonably regular. And we know that in the spherical case, the regular tessellations are essentially the Platonic solids, plus a few sort of pyramidal like ones. Plus a few more. And in the Euclidean case, well, then there's essentially squares and equilateral triangles and hexagons if we're going to tile with regular figures in the familiar patterns. But in the hyperbolic plane, well, there are lots. And the fact that there are lots means that it's somehow easier to choose one of those tessellations to fit particular surfaces that have already been cut up into polygons into the hyperbolic setting. So before that we do that, let's just introduce a little bit of notation just so we can talk about surfaces more efficiently. Let's talk about connected sums of surfaces. So suppose we have one surface M1 and another surface M2, and we want to combine these in some way to form a connected surface. Then what we could do is we could drill a hole in that surface, and we could drill a hole in this surface. And then we could just take that hole and sort of lift it out so that it's a little tube. And we could do the same thing for this one, little tube coming out. And then we could glue those tubes together. And so what we would get is, in this case, that's maybe where the tube is. So here's where M1 was, here's where M2 is, here's where they're joined at a little bottleneck. And this one we might call M1 plus M2. Just gives us a notation for describing surfaces pleasantly. So for example, the Klein bottle is the projective plane connected with itself. And so our fundamental theorem is that all the surfaces are either the sphere or a certain number of projective planes connected, or a certain number of tori connected. That just gives us some notation for talking about these things. So today I want to talk about two particular ones. So we're going to look at the two-hole torus. Have a look at that first, and then we're going to look at three projective planes. So the two-hole torus is what you get when you take a single torus and you connect it with another torus. And we're going to do a few cuts on this to make it into a bunch of polygons. So let's do some cutting. Let's say there's C1, and on the back side C2, and over here we'll make a cut E1 on top, and under the bottom E2, and over here D1, and on the bottom D2. So if we cut there, then we transform this into a pairs of pants. Not sure if that's grammatically correct, but so C1, C2, D1, D2, and D1, D2. That's like the left half. And the right half similarly. C1, C2, E1, E2, E1, E2. All right, now let me introduce just a few more edges. So I'm going to cut it a little bit more. So I'll call this edge A1, this edge this edge here A2, here to here, this edge A3, and similarly over here B1, B2, and B3. So if we cut along there, take the pair of pants and snip there, and snip there, then each pair of pants is going to fall into two pieces. And each of those pieces is a hexagon. It has 1, 2, 3, 4, 5, 6 sides. So we get 4 hexagons. 2 for each pair of pants. First pair of pants giving us these two. And the other one's giving us B3. C1, B1, E1, B2, E1, C2, B3, E2, B2, E2, and B1. Now at any one of these vertices, how many hexagons meet? Let's say at this vertex here. At this vertex here, well, the front and the back of this pair of pants obviously meet, but this point here is also identified with one of these points over here. So there's actually 4 corners of hexagons meeting at every point here. In other words, if we looked at the neighborhood of this point in the original business, there would actually be 4 of the hexagons coming together at that, or 4 corners, not necessarily 4 different hexagons, 4 corners meeting at that point. So to put these together, in a geometrically homogeneous way. So what we were interested in is, this is obviously not very homogeneous geometrically. So we want to give it a uniform geometry. Then what we want is to put these hexagons together, put together these so that 4 hexagons or hexagon corners meet at a point. Now in ordinary Euclidean geometry, the way we've got it here, these hexagons have a tangle of, well, that's I guess 120 degrees or 1/3. So if these are regular hexagons, then 3 of them will be arranged, but we can't arrange 4 of them, at least not in Euclidean geometry, to come together. So what we perhaps like to have is, we want regular hexagons with tangles of 1/4 at each vertex. So such a thing is not possible in Euclidean geometry, but it is possible in hyperbolic geometry. So let's have a look at our hyperbolic plane. There's our sphere, unit sphere. The interior is the hyperbolic plane. If we have 6 points which are very close to the center of the sphere, and they're regularly spaced, then the lines, the hyperbolic lines through them are pretty well straight lines, because these circles that are supposed to meet perpendicularly, if they're going through the center, they're almost straight lines. So they'll be almost straight lines, and these will be almost like a Euclidean hexagon. However, if we imagine blowing this thing up, there's the center, if we imagine blowing this thing up gradually and continuously to a bigger and bigger, also still regular hexagon, so at some stage we might have something like this. Well, now the great circles, the lines, look like this. So we're talking about a hexagon that looks a little bit like this now. And you can see that the angle or the tangle between the 2 vertices, lines meeting at a vertex, is no longer a 1/3, it's something less than 1/3. And in the limiting case, as we get very close to the boundary, let's just have a look at the very limiting case when we're actually very, very far away. Well, then what happens is that the great circle, big circle that goes through here, which is perpendicular, will be actually tangent to the one that's perpendicular there. In that case, the angle between these is going to be 0, no matter how you measure them. So in the limiting situation, we have actually angles of 0. Now that limiting situation is technically speaking not part of our geometry, but you can just imagine something that's very, very big, so it'll be almost like that. So here the angles is pretty close to 0. Here it's pretty close to being 1/3. and it's varying continuously. Okay, so that means that at some intermediate point, we should be able to get any value between 1/3 and 0. And that's the beauty of hyperbolic geometry. Even though it's a regular hexagon, completely regular, all the sides look exactly the same, all the angles are the same, nevertheless, there's this degree of freedom in what it actually looks like. So we can choose, we can find a regular hexagon with interior angles or tangles, turn angles, equals to 1/4.
On the sphere, don't you get the same property? But as you change the triangle or something, the angles change.
That's right. You could also go from sort of the Euclidean thing, but there the angles get bigger. Here the angles get smaller. Sort of the opposite kind of phenomena. The difference in here is that there's more room in the hyperbolic. In the sphere, we're kind of constrained by the sphere itself. Here there's lots of room, especially near infinity. All right, so we can find a regular hexagon with interior turn angles equals 1/4. And let's have a look then at what that means in terms of tessellations. There's a very pleasant tessellation then associated with such an object. Okay, so let's okay, so these are all supposed to be perpendicular. Okay, it would actually be a little bit smaller than that probably, but okay. Now, suppose I take this polygon. It's a symmetrical, regular hexagon with 90 degrees or a turn of 1/4 at each vertex. And suppose I start reflecting it. I want to make a tessellation just like as if it was a regular hexagon in the plane. So remember, if we're in a regular hexagon, we want to make a tessellation, we can just reflect the original piece in any one of the sides. You reflect, and you get another one. And then you reflect that one in there, and you get another one. But it's got to be sort of organized, so you reflect here, and you reflect here, then you get back to the reflection there. So these angles have to be such that they divide the total angle nicely into an integral number of pieces. But 90 degrees certainly does that. So if we reflect in the sides, what are we going to get? Well, it gets a little bit tricky to show, but it's going to be another hexagon. It's going to be something that looks roughly like this. 1, 2, 3, 4, 4, 5, 6. Something like that. Okay? So if you do the inversion, so what we're just talking about inverting in this circle or line. You do the inversion, which is the reflection. You calculate where each of these 6 points goes. You see, you end up with something, okay, that looks roughly like that. And this angle is also 90. And if we reflected it in this side instead, we would get, okay, and then if we reflected one of these in, say, that side there, we would get a fourth one, which just fits in the space up between these two. So there'd be one side, two sides, and then there'd be a 3, 4, 5, 6, be a little bit smaller. And we could keep going like this. You could, on each side, you could reflect the hexagon that you've got to get another hexagon. And the fact that there's a turn of 1/4 here means that if you do it 4 times around any vertex, you're going to get back to where you started. So you're never going to end up overlapping one that you've got in a wrong way. So you're going to get a tessellation of the hyperbolic plane. Get a tessellation with hexagons, into hexagons, with 4 meeting at a vertex.
And each of those are regular.
And each of those are regular. It doesn't look like it to us, but in the geometry they're actually regular, because each a reflection is an isometry. We've declared it to be an isometry, so that this thing here, which is the reflection of this, is going to be equal in measurement, no matter how you measure it, distance or quadrants or whatever. And the angles here, or the turn angles here, are going to be the same as the ones over here. Now, these 4 hexagons, well, they're 4 hexagons that meet 4 at a kind. So they're like a model, like these ones here. So we could take these and suitably impose it on here so that the things were all matched up. Then we'd still have some more gluing to do, but we could then we could think of our 2-hole torus as being this object here with edge identifications. Now it's sitting inside hyperbolic plane in a rather nice way, so there's actually lots of copies of it all around. So here's some kind of copy of our 2-hole torus. I'm going to do that with, the question is, can we do it with octagons? I'm going to do it in octagons in a second, yes. That's a very good question. Okay, so the question is, why don't we do it with octagons? And that's very natural. There are many different ways of representing a given surface in this way, depending on how we try to cut things up. But in our proof of our main theorem, we remember we got our standard form for our surfaces. So the standard form for our 2-hole torus was this: A, B, A inverse, B inverse, C, D, C inverse, D inverse. So we can try to put that into the hyperbolic plane, and here's how we do it. Remember that abstractly we have an octagon with sides A, B, A inverse, and so on. And we're going to want to glue that together. But remember that in the course of the proof, we arranged, this is the first proof, we arranged that all of the vertices were the same. Remember that? So that means that when we eventually glue this together, the vertex A is going to have 8 corners coming in. 8 corners coming in. And that means that we want to represent this with an octagon whose turn angle is 1/8. 1/8 of the way around. That way there'll be enough room to have 8 of those meeting at vertex. So let's put an octagon in here. 1, 2, 3, 4, 5, 6, 7, 8. So we're going to choose that so that this turn is 1/8. Can we do that? Well, yes, we can. This one here is a lot more than 1/8. as if we imagine putting this thing in a very near the center, it would be close to the Euclidean value. And then as we expand and the octagon approaches the ideal, or the boundary, the angles or turn angles approach 0. So some intermediate value, there's one position where we have still a regular octagon sitting inside here with an turn angle of 1/8. And that will ensure that as we reflect, it's a similar kind of story to here, but a little bit more complicated because there's 8 now, not 4. So we get 1, so if we reflected in this thing here, say, we would get 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 7, 8. The closer you get down here, the smaller the circles become. So this octagon and this octagon are congruent because they're obtained by reflecting in this circle here. All right, so it turns out that algebraically one can also describe these isometries, and to do that it's very convenient to work with a triangle. Just like in a regular octagon, this triangle here plays some kind of interesting role. The symmetries of the octagon are obtained by reflecting in the sides of this triangle. So this kind of triangle here, which has a 90 degree there, and it'll be that'll be, I guess, half of 1/8, so 1/16, and that'll also be 1/16. It's actually an isosceles triangle. Well, if the reflections in its 3 sides are given some names. So if that reflection is called R1, and that reflection is called R2, and that reflection there is called R3, then R1, R2, R3 are reflections in this sort of basic triangle. And it turns out that all the reflections that occur in this tessellation can be written as words in R1, R2, and R3. So there's a sort of an algebra of reflections, and I just want to give you a brief idea of how that might go. Let's have a look at the labeling of the sides. So let's call this one A and this one B. So this one will be A in the opposite direction, and that will be B in the opposite direction. A, B, A inverse, B inverse, and then C, D, C, and D. Yeah, that's the side A. Okay, so to see the surface as a space of orbits in the same spirit as we looked at the Klein bottle or the torus as a space of orbits, what we need is a group that generates orbits. Now, all of the reflections here are a little bit too much. We need to just choose particular special reflections. In particular, we need a reflection that sends this A edge to this A edge. But so that if we're going in this direction over here, then it corresponds to going in this direction over here. And that map, let's call it T sub A. How could we get that? Well, so what do we want to do? We want to send a point here, say some point that's close to the bottom of A. We want to send it to a point over here, which is close to the bottom of A. So how would we do that? So one way of thinking about what you do is, okay, it's R1, R2 squared. Let's think what R1, R2 does. If you reflect in R1, and then you reflect in R2, that's two reflections in two lines which are meeting. That's like a rotation. Okay? So this is going to be R1, R2 is a rotation around this point, around the center point. So it's a rotation R1, R2 by twice this turn angle. Okay, so if we do it once, if we apply R1, R2 to this point once, we'll get over here. That's what it'll rotate it, 1/8 of the turn. And then if we do it once again, we'll be over here. Now we wanted to get it over here, so what we could do is we could reflect it in R1. So followed by reflecting in R1, and then reflect in R3. R3 is the reflection in this side of the triangle. All right, so you can cook up in terms of, say, the generators R1, R2, R3. You can cook up transformations that take our basic polygon and act just like the translations did when we were constructing the torus. So we would also need a T sub B, a T sub C, a T sub D, corresponding to these other three edges, which are very similar. This is a transformation that takes this thing here and sends it over here. Well, maybe I should just do it like this. It sends it over here, it shrinks. Yeah? It's not orientation reversing. Its orientation is the same. So that edge A there ends up, pointing to that with this finger, it ends up like this. So it sort of matches up there. Okay? So that particular transformation that sends this to that is obtained from these ones by that formula. So the story is that the two-hole torus then can be thought of as the space of orbits. So the two-hole torus then has an incarnation as the space of orbits H mod the group generated by TA, TB, TC, and TD. And this makes it very homogeneous and means that any one point on the two-hole torus looks very much like any other point. And locally, we can talk about the hyperbolic geometry of the two-hole torus coming from this realization of it. All right, I'll just say a few words about, you can do this for more complicated things. It's something similar. The formulas can get quite involved if you actually want to write down everything explicitly, but you can do it. So for our 3 cross-cap surface, which was P plus P plus P, it had our standard form for it was A, B, B, C, C. 3 cross-caps. So we can try to do the same thing for that. And what we're going to need is a hexagon with 6 sides, 1 for each one of these letters. And how big is the angle going to be? Well, in the hexagon that we're going to use, A, B, B, C, C. Again, all of these vertices are going to be identified. And so there are actually 6 of these turns that are going to come together at one point. So we want to arrange that each one of these is 1/6. So again, we do that. We shrink or expand a small hexagon until we get a hexagon that has nice regular hexagon sitting symmetrically in the middle so that all the turn angles are 1/6. And that will ensure that if you reflect the hexagon in one of its sides, okay, you're going to get another kind of same kind of story, like that. And if you could also reflect it in this side, 1, 2, 3, you could do it all together 6 times, and they would fit together, something like this. 1, 2, 3, 4, 5, 6 of them fitting around one vertex. And they're all congruent. And they're all exactly the same as far as the geometry is concerned. And then you would have to look at the edges, A, B, B, C, C, and choose transformations that, say, allow you to identify this edge with this edge. Okay, but so let me do the copy over here. So we have to find a transformation that sends this to this, but that had the property that it sends this edge A in this orientation to this edge. Now, if you think about it, if you just take this thing here and try to do it without lifting it off the paper, when you move it down here and rotate it around so this A edge is down here, the A edge is going to be in the wrong direction. So you're going to have to actually flip it over as well as rotating it. Or to put it another way, in terms of reflections, if you write it as a product of reflections, there will be an odd number of reflections that are involved, not an even number. An even number of reflections will preserve the orientation. An odd number will not. All right, so that's a very brief introduction to a very rich subject. There's a lot of beautiful artwork I'm sure you've seen by Dutch artist Escher, who's a good friend of Coxeter's. Which uses hyperbolic geometry and these tessellations with many beautiful patterns. So if you search on the internet, there will be many interesting examples, and also very easy to find much better pictures than what I'm showing you here. In terms of just look for hyperbolic tessellations. You can find all kinds of patterns to see how there are many possibilities, and it's really intimately connected to these surfaces of negative Euler numbers. All of the surfaces of negative Euler numbers live appropriately somewhere in this hyperbolic space. So next time we're going to talk about knots. Okay? We're going to talk about knots and also about how surfaces come up in knots. So I'll see you then.